Section 9.6, the ratio and root tests. The ratio test is particularly useful for series which converge rapidly, such as series involving factorials or exponential functions. Now, for the purposes of this lesson, let us recall some things you need to know. Recall that 0 factorial is defined to be 1. So let's also remember that n plus 1 factorial is n plus 1 times n factorial. And let us remember that 2 to the n plus 1 really means 2 to the n times 2 to the 1. We're going to need all of these algebraic things we should know. Our next test is the ratio test. Let the sum of n terms be a series with non-zero terms. This series converges if the limit as n goes to infinity of the absolute value of the n plus 1th term over the nth term is less than 1. And it diverges if the limit as n goes to infinity of the absolute value of the n plus 1th term over the nth term is greater than 1. And our limit is inconclusive if our limit as n goes to infinity of the n plus 1th term over the nth term is 1. For all these examples, again, let me explain them, and then I'll give you a moment to write down the work. Determine whether the following series converge or diverge. Okay, the series as n goes from 0 to infinity of 2 to the n over n factorial. All right, our ratio test says to take the limit as n goes to infinity of the n plus 1th term. N plus 1 means everywhere you have an n, we're substituting n plus 1 over our actual series nth term. Let's do some algebraic simplification. This fraction divided by this fraction means this fraction times the reciprocal of that one. Okay. And what does 2 to the n plus 1 mean? It means 2 to the n times 2 times our n factorial. That's all in the numerator. This gives me, how can I simplify n plus 1 factorial? I can make it n plus 1 times n factorial times 2 to the n. Now let's look at what we have. I have 2 to the n times 2 times n factorial on top. I have n plus 1 times n factorial times 2 to the n on bottom. Notice my 2 to the n's cancel, my n factorials cancel, and we are left with this. And the limit as n goes to infinity is 0, which is less than 1. So by the ratio test, this series converges. Let's look at our next one. This is a good series for this test. Look at everything going on. So we know it's going to be the ratio. We got to look at the ratio of the n plus 1th term over the nth term. Let's look what happens. My n plus 1th term, everywhere there's an n, is going to go n plus 1. 2 to the n plus 1 plus 1 over 3 to the n plus 1. What does 2 to the n plus 1 mean? Well, it certainly gives me 2 to the n plus 2, but it also means 2 to the n plus 1 times 2 to the 1. Okay, that's going to be important. So here is our n plus 1th term over our nth term. Dividing by this means times the reciprocal. I'm going to go ahead and take advantage of the fact that I know 2 to the n plus 2 could be written as 2 to the n plus 1 times 2 to the 1. Why would I do that? Because my 2 to the n plus 1s are going to cancel. I'm going to do the same thing with my 3 to the n plus 1. Write it as 3 to the n times 3 so that my 3 to the n's cancel. And we are left with this nice little thing. Now, what is happening here? Well, notice that I have, this is n plus 1 quantity squared, this is n squared, so my degree is equal on top and bottom. So the limit as n goes to infinity is 2/3, which is less than 1. So my series converges by the ratio test. Okay, pause the video and take a moment to write down these two examples. Okay, so when we have factorials, usually ratio test is what we like to use. It's one of the best. So I'm going to look at my n plus 1th term over my nth term. And I'm going to simplify. This would be n plus 2 times n plus 1 factorial over 3 to the n times 3 times 3 to the n over n plus 1 factorial. You can see what cancels. This is what we have left. What do I get as n goes to infinity? I get infinity, which is greater than 1. So this series diverges by the ratio test. Take a moment to write this example down. The fact that the ratio test is inconclusive when the n plus 1th term over the nth term goes to 1 can be seen by comparing our two series, 1 over n and 1 over n squared. In both cases, the limit as n goes to infinity of the n plus 1th term over the nth term is 1, but we know that the first series diverges and the second series converges. Okay, our last test before the test is the root test. So the root test works well for series involving an nth power. And let's just remember how those roots work. We know the fourth root of x to the 12th would be the same thing as x to the 12 fourths, which is x to the third. But the beauty here is really this piece. This is x to the 12th to the 1/4, and that's the property we're going to use. So let my series be a series with non-zero terms. It converges if the limit as n goes to infinity of the nth root of the absolute value of my nth term is less than 1, and it diverges if that limit is greater than 1. And again, another test where it is inconclusive if it equals 1. Now, let's remember, since our absolute value is involved, you can use this test on a series with negative terms because we are taking absolute value. All right, the series as n goes from 1 to infinity of e to the 2n over n to the n. Oh, wow, that's a weird one. Again, let me explain the examples, and you'll pause the video to write down the work in a little bit. So first of all, we're going to use the root test, n to the n. We're going to first of all take the root, do our root test, and we're going to write this as e to the 2n over n to the n to the 1 over n power. This means e to the 2n over n to the n over n. We can simplify those exponents. That gives us the limit as n goes to infinity of e squared over n, which is 0, which is less than 1. So this series converges by the root test. All right, let's look at this example. So if this did not have the plus 4, we would have a geometric series. But it does have the plus 4, and so now we have to do this differently. The nth root of 3n plus 4 over 2n to the n. And let's remember, that means that we have this raising each part to the 1 over n. When we do that, we get 3n plus 4 over 2n. The limit as n goes to infinity is 3/2, which is greater than 1. So we diverge by the root test. Okay, take a moment to write down these notes. Example number 6. So what we have here is, because of this, we're going to do the nth root. We have the limit as n goes to infinity of the nth root of n cubed over 3 to the n, which gives us the limit as n goes to infinity of n to the 3 over n over 3. Now, L'Hopital's rule does not apply. We are not in indeterminate form here, so we cannot do L'Hopital's rule like we've done with other problems. So let's see what we can do. This third down here is 1/3. So I can rewrite this as 1/3 the limit as n goes to infinity of n to the 3 over n. Well, now what? Well, let's make our notation a little simpler by calling this whole thing here y. And so we are going to let y equal the limit as x goes to infinity of x to the 3 over x. Now you'll notice we are probably going to want to take the log so we can bring this down. Okay? And we know that the log of a limit is the limit of the log. So we are going to take the log of both sides of this equation. And since the log of a limit is the limit of the log, we are going to, on this right-hand side, bring our limit notation out and take the limit of the log of this function. Now the log allows me to bring this exponent down. And so what we have here is the limit as x goes to infinity of 3 ln x over x. Now, L'Hopital's rule applies. Okay, this is indeterminate form. And by the way, don't forget to look at section 8.7 for other indeterminate forms. But primarily for this course, we will really just be looking at the 0 over 0 and infinity over infinity types. But there are many, many more. And so what I can do from here, then, we know that we can show that L'Hopital's rule applies. So now what we have here is the natural log of y is the limit as x goes to infinity of 3 times 1 over x, all that over 1. As x goes to infinity, this side goes to 0. And log is exponent. What does it mean when we say log ln y is 0? That means that e to the 0 is our y. And what is e to the 0? That is 1. So now I can go back up here and substitute 1 in. And 1/3 of 1 is 1/3, which is less than 1. And so this series converges by the root test. Okay, take a moment to write down this example. Now you will notice on this next page are several examples that you will work. And I will give you the answers in class. On the next page, something for you to read, strategy for testing series. There's lots of things. You want to read through this page and make a note of all the very good information that's here. The only way to become skilled at evaluating series is practice, practice, practice. Sorry, not sorry. On the next page, one of the books I use as a resource is Anton. He's the author. And he's got a really nice table of this test. Here's what it says. And here are comments about when to use it. You definitely need to know the conditions for every test. The next page, 108, our textbook has this table in it. Again, what the test is, what the series looks like, when it converges, when it diverges, and comments. And then Finney, DeManno, Waits, and Kennedy, it's another calculus book. This is a wonderful flow chart of how I can determine convergence. Then on the next few pages, we have a really nice write-up of a series applications. Okay, and these are really, really good. It's easy, gives some very good explanations. Be sure you take the time to read through it. Your TPs for section 9.6 are 13, 19, 37, and 39. See you next time.